Right. Well, I'm here today to talk to you about a thing called Argo, which is a new introduction into the latest version of Xen, Xen 4.12. And I just want to give you a talk through what Argo is, where it came from, what the key properties of it are, its relationship to other hypervisors, and then a bit on the details, and then some references. So Argo is an inter-domain communication transport. It is a means of transferring data between VMs running on the same host. And it was developed originally for Xen Client. It's been around for an extended period of time. It was known as v4v when it came into creation, and subsequently v4v has been developed and extended and is incorporated in Bromium's vSentry product and is deployed on millions of machines. Whereas Argo has been produced, derived both from v4v, the original technology from Xen Client, and with some input from the Bromium extensions, but it is now its own thing incorporated into Xen. And in a nutshell, the one-line description of it is that it is a hypervisor-mediated data copies from one VM to another. And the reason for this structure is because it prioritizes isolation between your VMs, the ability to enforce access control policies on your data connections, and ensuring that there is conformance to the transfer protocol, that the receiver can trust that the way that the message is delivered complies with expectations. And it is a simple but powerful primitive that you can build more capable levels of software upon. And as I mentioned, it's included in Xen 4.12. You set a kconfig option to turn it on into your build, and then there's a Xen command line option that you provide that tells the subsystem to come live when you boot. So Argo is actually the longest patch upstreaming in Xen's history ever, taking 8 years as far as I'm able to tell. So this is the timeline of what it looks like. Xen Client starts in 2010. And v4v, the original version, was developed in support of this software to meet the requirements of not wanting the network stack to be necessarily involved in your inter-VM communication. 2011 is when I think the clock starts. That's when Ross reserved hypercall number 39 in Xen. Jean produced a patch series, several iterations of the patch series of v4v submitted to Xen Devel. You can find it in the archives. It's good, interesting reading. A lot of input from a lot of people. Phil prepared a presentation at the 2013 Xen Summit. Ross picked up from where Jean handed over with another round of patch series. 2014, the OpenXT Project begins. It's sort of Xen Client's body of code is now open to the world, public. I gave a presentation in 2016 mentioning that we would quite like this patch series to go in. In 2017, Bromium's hypervisor is shipped on HP laptops, so this software actually gets deployed to millions of machines that don't even necessarily know that this is the foundation of it. And then in 2018, I posted the Argo patch series at the end of the year and through the early stages of 2019. 8 rounds of reviews and an iteration there, and finally it is been accepted into Xen. And it doesn't stop there. We're still working on the next aspects of Argo's development and capabilities. So there's a couple of related things with Windows. So Windows has had a similar capability at least since 2006. I'll touch on that in a bit. And the modifications to the QEMU machine type are kind of of similar interest to this. So Argo, it is one hypercall as far as Zen is concerned, with 4 basic operations. We register ring, unregister ring. That's where I'll talk through this a bit later, but basically if you're wanting to establish the ability to communicate, you reserve a region of memory and you let the hypervisor know, and then there's these 2 other hypercalls to actually, hypercall operations to operate it. So the key properties for Argo, and these are so important that's why we have persisted in attempting to get this technology accepted into Zen, because nothing else will do. These are properties that will continue to be maintained in future iterations of Argo. So there's no memory shared between guest VMs that are communicating, right? It really is the hypervisor that performs the data transfer between your 2 communicating endpoints. The data is copied. There's no shared memory, but it is actually a copy operation in order to maintain spatial isolation between your guests. I said it's the hypervisor that performs the data copy, and since the hypervisor is performing the copy, it's trusted to adhere to the transfer protocol. The write into the guest, will take into account ring indexes and behave as you expect it to, because you can trust that it's the hypervisor that's doing it. You're not dependent on the remote endpoint to play nice, and that's a contrast to, for example, the grant tables, if you were to use those. Anyway, so those are the key properties that make it distinctive and we will be preserved. And part of the reason that we care about those properties is due to this set of principles that are a foundation for resilient, secure systems. There's a body of research and work on what you look for in the structure of a system to enable you to build it into a thing that remains secure. And so this set was published in 2005. Data isolation, control of information flow, temporal separation, so that if there's any sharing of resources, you ensure that the resource is cleaned before the next tenant gains access to it, and fault isolation, because you don't want cascading faults to be able to, or failure of one subsystem to degrade another that's meant to be isolated from it. So Argo and v4v before it was built with these things in mind, and so the objective is to provide a strong foundation for communication. There's no shared memory. It does not require the grant tables. It does not require Zen store. And by removing the requirements on those things, you can build things that you otherwise would not be able to. So in order to create some kind of abstraction to say there's kind of a rather than talking about the specifics of Argo, the more general case of what is it about Argo that's different, and is this difference present in primitives provided by other hypervisors? I was trying to distill what it is that is different and distinctive and that you need to look for when you're evaluating, can I do the same thing elsewhere? So this hypervisor-mediated data exchange is the term we use to describe asynchronous authenticated message passing with no shared memory and able to enforce the adherence to the data exchange protocol. So this diagram might help make that concept a bit easier to follow. But what I'm really looking for here is that in order to get data from the sender to the receiver, it's the hypervisor that performs the transfer from one partition to another, so that the conformance to the ring protocol can be trusted because it's the hypervisor, the trusted entity that performs it. And in addition to the data being received at the receiver, there's metadata with it indicating context about it, so that the hypervisor provides assurance that that data originated from this VM. So there's an identifier, and there's also, you know, a size indicator that you can trust, because the hypervisor will tell you how much data it moved. So covering the existing interpartition communication, if we look at what's in Zen prior to Argo, you're using the grant tables and the event mechanism. So grants are typically used to establish shared memory regions. There are grant primitives that can do a data copy from one VM to another. But as the receiver, you don't have any guarantee that the data copy that was requested was going to adhere to the ring protocol. You are there is less context provided with the data that is copied. I'll come back to the additional context a little bit later. Another aspect of, while we're talking about grants, is that the grant table code has accumulated quite a lot of cruft over the time that it has been in use. Right, it was written by me originally, and as the Zen community learned more about, you know, performance or the types of primitives that would be wanted in order to support the PV drivers, different sub-operations were added, and it's quite an extended set of operations in the grant table code, some of which are not in use by modern PV drivers. There's also, at least on Intel platforms, 2 different APIs to the grant tables, which you can, I guess, can switch between them at runtime. And it changes the layout of the shared memory region. It's really not necessarily a good idea. And the grant tables in a paper published a couple of years ago were attributed for 5%, being responsible for 5% of Zen's XSAs, CVEs. And the most recent of those was actually yesterday. So anyway, in OpenXT, we apply a couple of patches to kconfig your grant table implementation down, and I would recommend those to anyone else who has an interest. Okay, so Hyper-V's interpartition communication. Hyper-V does have a method of sending data from one partition to another that conforms to that HMX structure. It has been there, it was documented in WinHEC presentation 2006. It's in the hypervisor specification document from Microsoft that you can find on GitHub. And again, it has a slightly different structure to Argo in that there is a copy into a private hypervisor region of memory and then a secondary copy into the receiver. But it is still the hypervisor that's performing that final delivery. And then Uzen. So Uzen is a open source type 2 hypervisor developed by Bromium that uses V4V, which is you can trace its lineage back to Zen client. And since it's open source, I studied the V4V implementation, studied the OpenXT V4V implementation in order to construct what Argo became. Anyway, V4V Uzen has no legacy PV interfaces. They're in this platform, guests use V4V in support of the PV devices. So there's no grant tables, there's no Zen store. It's all built on this simple data copying primitive, and this demonstrates that you can get away from Zen's problematic legacy interfaces with using an approach built on Argo. And yes, Argo, being derived from V4V, is also HMX compliant. So to walk through the operations that Argo implements, the first one, ring registration. This is where if you have you want to start a service that can have other VMs connect to you, you register a ring of memory with the hypervisor, with this hypercall op, and you specify either I want to receive messages from this other particular domain, or you can say I'm willing to receive messages from anyone. When you make this hypercall operation, XSM is checked to make sure that you're allowed to register a ring, or you're allowed to register an AnySender ring. And if it passes, then that ring's registered, and it creates a mapping in the hypervisor address space so that no matter which VM is scheduled, the hypervisor can still perform the writes into the ring and keep it nice and fast. Unregistered ring, again, when your VM decides I'm done with it, you can say I don't want to be receiving any more messages, and it's the hypervisor state's purged, and you won't receive any more data in that ring. The sendv is a synchronous operation. The guest sending data indicates the destination ring that you want to send to. So you identify the domain and the port, and you provide access to the data that you want to be sent. Again, there's an XSM access control check. There's a space check to see is there data that will my data fit? And if it does, there's a synchronous copy into the destination. If it doesn't fit, the hypervisor makes a note of, okay, this guy wants to send data there. I will give that guy a nudge when that level of space becomes available. So there's the fourth call is notify. This is for where a VM can query a receive ring in another guest to say, is there space in there? There's an access control check. You're only allowed to query rings that you would actually be allowed to send to, and you'll get back a state indicator, saying either you've requested, too much space, the ring's not that big, or yes, it's going to be fine, or there's too many people talking to this ring right now, you should come back when things are quieter. And again, the hypervisor will register interest. If you've said I want to send a large amount of data, it's not available, you'll get a nudge RQ later on when there is space available. And that's it. It's not a very complicated set of operations, but it does enable a different structure in your guess. It has full XSM Flask control over whether or not you're allowed to access Argo at all, whether you're allowed to register rings, and if so, whether it's to a specific endpoint, or whether you're allowed to register these sort of wildcard receiver rings. And similarly, there's a check on send, just to make sure that you have permission. So these are the use cases we have for Argo in OpenXT at the moment. It enables basically a seamless replacement of network transport between VMs. So anywhere where you think I want to send a data stream between VMs, Argo is a viable use case. So we export the user interface from the control domain to the actual UI renderer domain. All of that data goes over an Argo socket. Yeah, a series of different use cases. The last one, debugging support, is really handy. You can have an SSH terminal. You can establish a connection to the remote VM if it's got the service listening, and you've got interactive access to the other VMs on your system. This is what it looks like to do exactly that SSH use case. So in the VM where you've got your server, you load the kernel module, which knows how to talk the hypercalls to the hypervisor. You export this environment variable, which is then toggles the behavior inside this user space library. It's a preload library that enables you to run an unmodified SSHD binary, and it translates all the network access into Argo access. So, and it'll just sit and listen on the port specified. And then in your in your VM where you've got your clients, you do a very similar thing. You load the kernel module, you tell it in the environment, I'm going to be using Argo transport, and you use an unmodified SSH client binary to the address. The address gets translated into the domain ID of the VM you're actually trying to SSH to, and the connection gets established. And then, yeah, if you do this, you're basically typing at a regular terminal. Same as if you SSH'd across the network. This is kind of what that looks like as far as components. You've got your SSH server process doing system calls to the Linux Argo device. The kernel driver is then issuing hypercalls and invoking the hypervisor. Any nudges that come back for, hey, you've got an event or there's data waiting for you, come through the VRQ. And so at the point, yeah, rings are registered here. So the Linux kernel driver will register a ring for memory. The client on the other side, when it will connect, and another ring. If you're following the typical socket, accept, spawn another ring. It's a private point-to-point ring at that point. So the any sender ring is used, to accept incoming connections, and the point-to-point ring is used for the transport from once the accept call is.
So your libArgo then replacing the socket API calls? Is that what's happening?
That is what's happening. Yeah. Yeah. So all your socket invocations work. This interposer library. There is if you actually want to code directly against the Argo interface, you can. Yeah. It's just the interposer library makes it convenient because you don't actually have to change your existing binary.
Kind of like how your dbus thing you mentioned earlier too kind of works.
That's right. Okay, so this is basically just a specialization of the diagram I showed earlier on about HMX. When you actually have, Argo working this way, it's the hypervisor performing these data copies into the registered ring buffer. So that's Argo up to this point. The focus until Q1 this year was really getting the existing implementation into Xen at last, but it's not where we want to stop. There's a series of additional extensions to Argo that we have been working on the design for, and I can walk you through some of this. The sender domain context, this is about providing extra metadata in that header. So when the message arrives in the destination, you actually get the XSM security identifier of the domain that sent it to you, so that you can reason about where this thing really came from. It's basically enabling reasoning about XSM policy inside your guest. And if you take that further and you match your XSM policy with your SE Linux policy at either end, you can start to reason about which process at the other endpoint is talking to which process on the receive point, and start to enforce stronger policy controls. So this is the hypervisor plumbing to put that in. So the next step is, at the moment Argo implements unidirectional transport, but in order to apply narrower policy controls over the replies to that, you want to be able to track connection state inside the hypervisor. It's so we've got a prototype of that. It's just adding a bit more state to ensure that replies go to the same place that the original message came from. So yeah, building on these two things, we're looking to extend make a richer access control implementation and set of tools for managing a firewall. There's a very basic implementation if you need one now in OpenXT, but this will be a lot more powerful with these additional two things implemented first. The fourth thing is enabling Argo to establish communication between VMs at different levels of nesting. So the structure of Argo is actually a very good fit for communication between different nesting levels. Since you're invoking the hypervisor, it just needs some work done on how exactly do you name the other endpoint that you want to talk to, and again, there's going to need to be some policy enforcement that makes sense for that. Fifth thing, wildcard rings, protection of client forward progress. This is sort of more of a cleaning up item of a. At the moment with Argo, you can register a ring and say, I'm going to allow any domain to send to this ring. Now, the issue with that is you don't want a noisy guest to be able to deny access to other VMs to that ring. You want some means of enabling anybody who wants to communicate on that ring to make some forward progress. So that's one of the reasons why, at the moment in the current Argo implementation, there's two sets of policy controls. There's one for point-to-point rings, which are safe from that, and there's an additional policy control over who can register any sender rings, just to make sure that you really do know what you're doing before doing that. The last thing is I'd like to implement, using the term shutter rings. This is basically when you register a ring with Argo at the moment, it adds that ring to the hypervisor address space. So it doesn't matter which other guest is scheduled at the time, right? You can still make the hypercall send operation and get that data into the ring. It's nice and efficient. However, leaving your rings mapped at all times isn't necessarily what everybody wants if they're concerned about speculative execution, the ability to read memory. So this is just a policy control for saying, actually, for this ring, I'd like it to be mapped and unmapped only when it's actually in use as a confidentiality improvement. A few research items I'd like to do. First one is looking at some accelerated transport options. There's features of modern Intel hardware it would be nice to be able to take advantage of, perhaps in order to gain a bit more throughput. It's moving away from necessarily relying on the hypercall to send. VM func could be interesting, and that fits with the interest in an asynchronous send primitive. It might enable the use of Argo in wider use cases. Third thing is, at the moment when there's a notification of space available in an Argo ring, it basically notifies anybody who's ever said, I like this ring, I'd like to know when I can send something to it. So it's a broadcast, or there may be excessive wake-ups given that possibly only one of the people that you're waking up will be able to consume that space. So some research to do there. And then the last thing is integration with memory encryption technologies. This shouldn't be terribly difficult, given that it's the hypervisor that you're asking to perform the data copies. But we'll see. When Zen gets memory encryption integrated, it would be interesting to see whether there's anything that needs to be done to make this work with that. I'd like to, I've got a few references to further places where you can find out more about this, but this one's number one on the list and strongly recommended. It was a presentation delivered at the Platform Security Summit last year by Ian Pratt, the founder of the Zen project and the CTO of Bromium, and it's a retrospective of the lessons learned about hypervisor security over the iterations, beginning with Zen, going all the way through to Bromium's latest tiny hypervisor with a specific focus on security. So please do take the time to watch that video. And yeah, I've included on my final slide a whole bunch of clickable links for everything I can think of that is referencing this. Places to go for the code, places in OpenXT where we use it, documentation, useends, v4v implementation at the OpenXT source code repository for that. I think that's me at the end of my presentation. I don't know how much time I have remaining.
So
Okay. Sorry, there's a mic.
Sorry, I can project. Just real quick, when you talk about memory recursive technology, were you referring like SGX and things like that, or something else?
Yeah, or AMD's equivalent. Yeah, I have not. There are other experts on that.
So I see potential integrity benefits from this for dealing with like potentially not memory corruption safe people at the other side of the ring. But from the confidentiality perspective, this seems like kind of an exercise in. There's lots of cooperative side channels through speculative execution and like just architectural things which aren't going away anytime soon. So is the goal of this to, what is the confidentiality model that you're assuming on the hardware that you're running? Like, what is the goal, just to limit the bandwidth of?
No, it's to the ability to enforce access control over when you establish a connection between VMs, basically a yes or no, and to enable one end of a connection to have the ability to reason about who's on the other end with the connection information described by an entity that it trusts, right? So the hypervisor is a better place to put your trust than a random person on the other end of some shared memory.
But with grant tables, you also grant with some explicit domain ID, so you have that information, right?
You do, but I mean, for the grant tables, for example, you could have a domain reincarnated with the same domain identifier, whereas your ring will be torn down if the other end of the endpoint is different.
I was about to ask that, because when you just send to a DOM ID, right?
You do. Well, actually, in the current implementation of Argo, yes, there's the vCentry Bromium implementation of V for V has a very simple name service, actually. You can specify a UUID, which can map to the control domain, or it can map to my subdomain right now, right? And that's where the data will get sent. So there's no opportunity for looking up your domain ID, things changing, and then you using that domain ID and it goes somewhere you didn't want it to.
Exactly. So yeah, exactly. It cycles round. You just send to the domain ID. You have no idea who that is.
Right.
So presumably, do you also get, as part of the notify, do you get told if if you're waiting for space in a particular ring, do you get told if that domain's actually now gone away?
You'll never get a notification. So what happens is that hypervisor state gets torn down when the ring goes away. All of the pending notifications go away too. I don't think there is a notification you'd have to find about via some other means that your endpoint is gone. So if you try to send to that ring, you're going to get an error.
So the notification when the other side go away is something that we also have problems with VJAM, and in practice it was very important to have something in place to work around, because domain crashes. So.
Yeah. So basically, if the client ever issues a notify call, it's going to get back a no. That's not there anymore. Yeah.
I just have a couple of suggestions. So one is we have a super detailed design doc on the code written by you. I think it's excellent.
Okay. Thanks.
I think it would be beneficial to have a shorter, simpler interface document for an DOM-U implementer, so that you could provide a one-page document, because it is a pretty simple interface. But you could provide a one-page document, say you want to use this interface. This is a spec. This is a standard. Given that it has a new weight in virtualization of the standard.
Sure.
The other one is, do you know when the mem copy is performed, to which DCQ the time in Zen is accounted?
It's the sender. The time is accounted to the sender because it's a synchronous operation. So the hypercall, the sender issues the hypercall, the synchronous copy that happens then, that's the mem copy. So yeah, it's going to be counted to the sender.
Anything that can block that synchronous call in the mem copy, or is it pretty like just goes?
So if, for example, you provide memory that the hypervisor isn't going to be able to read, let's say that you give it a large buffer and only the start of that buffer is actually valid. It's going to find out halfway through that you've given it some rubbish. And so you'll get I'm pretty sure you'll get a hypervisor log message that the sending guest is doing stuff it's not really supposed to. The operation call will fail.
Okay, so like I'll return an error saying.
That didn't happen. Yeah.
Okay. Is there anything that's type specific to x86, or is this pretty generic enough for ARM?
It's implemented in ARM too. Okay.
Question related to this V4 tables. So you can specify some policy what domain could talk with what other domain dynamically.
Yeah, so this is the V4V tables which OpenXT carries that's not in Zen. And one of the reasons it's not in Zen is because it's a good fit for the OpenXT use case because we're pretty locked down. We only use, so all of our use cases are between platform VMs. And so we've got more confidence in those than the running guests. And yeah, you do. In the V4V tables, you specify this source and destination can talk to this other source and destination. You basically the domain ID and port pair. One of the challenges with it is with the wildcard rings, where all of a sudden it's fine for sending it to the wildcard ring, but in order to be able to reply, you've got to open up that firewall for anybody who can send to it if you want to generally allow a service to be accessible by any VM, which is not the case where we're using it.
So you can update this policy at runtime.
That's right.
But can you also force to tear down existing connections at runtime from toolstack or .0 or whatever?
You could, no, it won't force it to be torn down, but you can add a rule which basically says this connection's not allowed anymore, at which point any send operations are going to hit that firewall rule. So in effect, you accomplish the same thing. The ring's still registered, but there's no data going if you don't want it to.
Okay, what is performance impact in practice? How many copies are there when you are measuring it from one user space to another user space?
I think there's just the one. I'm less familiar with the Linux driver implementation than I am with the hypervisor implementation. Eric is a chap who works on OpenXT who's working on the Linux driver. We're in the middle of writing a new one to use the VSOC interface rather than the existing character implementation that we have. We've got one that works for now. We would quite like this VSOC one. I don't know whether Linux is doing copies inside the kernel. I don't necessarily see why it would need to, but there's definitely the hypervisor doing a copy from the source to the destination.
So do you have some benchmarks for this?
No, I don't.
Okay.